All right, we're going to start section 5.1, the natural logarithm. The derivative sheet that we just worked on, please feel free to have that out. You may want to reference that from time to time and have that with you. If you will keep that sheet clean, you will be able to use it on certain portions of exams later on. So as long as you don't write anything extra on there, sample problems or something like that, you can use that sheet in the future, okay? So the first thing we're going to talk about today is, this whole section is called the natural logarithm, and we're going to talk about differentiation. So the first thing I want you to remember is a rule that you just wrote down, and you told me what it was. So what was the second? Well, I think we had the second one. What was? Well, we didn't write this one down. I lied to you, but I'll show you why in a sec. We're going to look at an antiderivative rule. Do you remember what the antiderivative rule of? So we wrote the derivative rule of the power rule on the board. Do you remember what the antiderivative rule is for that? Yes, Jordan, right? Yes, okay.
It's x over n, and x to the n plus 1 over the original n.
Yeah, some variation of that, right? All right, there was a condition. All right, there was a condition when you learned this rule, and the condition had to do with what n was allowed to be. Do you remember there's one number n can't be? 0 is actually okay by kind of default. It's -1. The n cannot be -1 here, because what would happen if n were -1? You'd divide by 0. Well, no, you'd still be dividing by -1. But what would your exponent be? Your exponent would be 0. And what happens when you have a 0 exponent on something? It's 1. Anything with a 0 exponent is a value of 1. So if you had like 5 to the 0, that number is 1. And that would end up giving you the number 1 on top and the number -1 on bottom, and the antiderivative would be -1. And that actually wouldn't work. And if you looked at a graph of this, you would have issues with it immediately and say, that's not right. There's something wrong with that. So what if, in fact, n is equal to -1? Well, if n is equal to -1, then you'd actually have the integral for x to -1 like this. But there's another way that you have learned before to write that. How else can you write x to the -1?
Can you take it on the outside of the...
Nope. This is an algebra question still at this point. 1 over x, yes. So one of our exponent rules from way back, ages ago that you've seen, is that when you have a exponent of a negative, you can actually pull it down to the denominator and make that exponent positive. In this case, the exponent of +1 just sort of disappears in terms of what you see. And so then you have this integral of 1 over x. And prior to now, if you've only had through Calculus 1 with the textbook we're using, you haven't seen this happen before. So what then? Well, let me clarify also that this is only good when x is greater than 0. And you have some details on your sheet. I think they're on my next page. Let's see. Okay. Things are not working well, are they? And what happens is we actually end up with the natural logarithmic function. So this is actually a function you have seen before. You saw it in probably a college algebra or pre-calculus kind of a course. You saw a function that was called ln of x. It's natural log. So you might think, well, why did the L come before the n? Because that's natural log, and that's an English issue. We modify we do our adjectives modifying our nouns. I think I got that right in English. We do it backwards of many other cultures. And so we have natural log, and we are going to write ln of x. And that's actually defined to be the integral of 1 over x dx. I mean, that is the antiderivative. And the reason that this matters is because we actually haven't seen, up to this point, how to take a derivative of the natural log. And actually, natural log is defined to be the antiderivative of 1 over x. The domain for this is actually the set of all positive real numbers, and some books will actually denote this with an R with a double line on the left and a plus. So the r with the double line on the left is usually the real numbers, and the plus just means all the positive real numbers. So the only domain values that we can use are positive x values. Okay? So I'm going to show you a few things about the natural log function that you've seen before from an algebra perspective before we jump into the derivatives and the calculus perspective, okay? So some graph features for you to jot down. So here is a graph of ln x. All right, so some features on this. It has an x-intercept, and if you can see it, it's right here. And this value is actually at the value of 1, so it actually crosses the x-axis at x equal to 1, y equals 0. There is no y-intercept. It will not cross the y-axis. And the reason it won't cross the y-axis is because there's a vertical asymptote there. So at at x equals 0, it has a vertical asymptote. That's the y-axis. It is increasing without bound. So what does that mean? Well, it actually means something you've seen before, again, from calculus. It means that if you were to talk about limits, which I'm sure was one of your fun and favorite things that you did in that course, that the limit of the ln of x, of the natural log of x, as x goes to infinity, is actually infinity. So if you were to take a look at the left-hand side of this graph and keep going out, there is no upper bound. There is no sort of location where I can say it's not going to jump up above this horizontal line. It's always going to keep growing bigger. Very, very gradually, very, very slowly, but it's always going to keep getting bigger. Okay? The domain on this, can you tell me, what is the domain for this function? What x values do you see? Positive real numbers. And there's a couple of ways we could write that. So we just saw one notation that looked like this, right? Another notation that you'll see used in lots of books is you'll use interval notation, which looks like this. So you have parentheses to indicate that you can't actually equal those values. I can't equal the x value of 0. There's an asymptote there. I know x can't be 0. And infinity is not actually a number, so I put a parenthesis on that side as well to indicate I can't equal the value of infinity because it's actually not a value. So it's kind of like a starting point and an ending point, and the comma in between says that the stuff happens between them. Okay? What about range? Range is the y values. What range values do you see on this graph? Negative infinity. Yeah, I mean, it actually comes way down here. You can't see it, but it continues down below, getting closer and closer to the y-axis. So it goes down to negative infinity, it goes up to infinity. So another way you could write that is that it's the real numbers, if you would like. It's continuous. One of the ways you've probably seen continuous described is this idea that you can draw it without picking up a pencil. Has no holes in it or gaps or jumps. It's also one-to-one, which means that if you give me an x value, there's exactly one y value that goes with it. Right? And if you give me one y value, there's exactly one x value that goes with it. There's no duplicate values anywhere. And then another feature that you talked about in calculus was about concavity. This is actually concave down. It's kind of opening downward, sort of like a bowl shape downward on this one. So the first thing that we're going to do is we're going to actually sketch the graph of something, and we're going to do this using some things that you know from college algebra. So the graph that we're going to sketch is the function of negative natural log of x plus 2. So you see the natural log of x in there, but you see that there have been two things that have happened to that graph. Can somebody tell me what that negative does? We'll start with that one. Nope. Nope. What is it? Well, it's already concave down. It flips, what was that, Jordan? Okay, so it flips it around an axis. So anytime you've got a negative affecting something, like a multiplication by a negative, it's either going to flip it up and down or left and right. Okay? So when the negative's on the outside of the function, that flips things up and down. All right? So this is going to actually flip our graph over. So instead of being concave down, like Chelsea mentioned, it's actually going to be concave up when we're done. Okay? If there were a negative inside like with the x value, it would flip it around the y-axis, and we'd have a horizontal flip instead. Okay, that's what that happens. So this right here will be what's called a vertical reflection. Okay, so Janet mentioned moving things left and right. That 2 actually has that feature. Do you remember what adding a 2 will do?
To the left, it's opposite.
It's opposite when it's inside. Yeah, I mean, our gut reaction says positive 2, move it to the right. Anything that happens inside actually does things opposite. So if you have addition of 2, it's actually going to move it left 2. If you had subtraction of 2, it would move it right 2. So this we're going to actually see that shift, let me write that down actually, it is a shift left. All right, so in terms of a graph, we're going to have our XY axis, and we're going to end up having a new vertical asymptote. Where will our new vertical asymptote be? Before it was on the y-axis.
Left -2.
It'll be left at x equal -2. So we're going to have it somewhat like over here. And let me mark between that we have a spot here. So this is x equal to -1. This asymptote then is at x equal -2, which we'll label. Doesn't look much like a negative. Let's try again. And again, normally it would have a concave down feature, but we've got a reflection going on, so it's actually going to have a concave up feature. So it's going to flip everything across that x-axis, right? We're going to flip it over. So it actually keeps the the x-intercept in the same location. So before, our x-intercept was at over here at 1, right? Don't know why that's so heavy. We'll change that in a second. And that actually will also move left too, just like everything else did. So where's my x-intercept going to be? At -1. So it's going to be right here. And instead of it going from the bottom of the graph to the top of the graph, like it did, we're going to flip it, so it's actually going to look something like this. So far, so good? Okay. And of course, you're welcome to confirm that with a graphing calculator. You'll see that it will do the same things for you. The things that it won't do is it won't put that dotted line in there on your asymptotes, so you have to sort of understand that that's what's going on and know exactly where that's going to occur. What's the domain for this? Okay, -2 is where it starts. Remember, we want to talk about x values. The smallest x value is -2, but we can't actually equal -2. We can get really close. We can actually get there because there's an asymptote there. And I can go all the way to infinity, right? So my domain is actually -2 to infinity. What's the range? Yeah, the range is still all real numbers. It didn't change because I just flipped things vertically, right, like this. So, all right, some log properties that you may not have seen or thought about in a while. I suspect it's been years since you've seen some of these log properties. The natural log of 1 is 0. Now, that should make sense if you take a look back at that graph that we did originally. Because the original graph, when x is equal to 1, what was y? 0. That was an asymptote, right? So if you actually looked at plugging in over here, I'll get that back to that screen in just a second. Whoops. One too many. If you actually looked at plugging in x equal to 0, so this said natural log of x equal to 1. If you plugged in natural log of 1, you'd actually get 0. It's the x-intercept. The natural log of e is actually 1, and we haven't talked about logs in general yet, but what you might remember is that natural log of, we'll say e since it has it here, is similar, or another way of writing it is with the actual word log, with a base as a subscript of e. And there is a e there that was from the original e here. That just moved to here. And whenever the subscript for the log, the base of the log, and the inside of what the log is taking the value of match, you actually get back the number 1. And we'll talk more about altering that to see that happen later, but the natural log of e is 1. The last 3 are the most helpful for what we're going to be working on. And from a derivatives and an antiderivatives perspective later, if you have the natural log of a product, that's actually the same as the sum of the natural logs of the two pieces. Okay? That's not a derivatives issue. I didn't take any derivatives. I'm not doing any calculus. This is still algebra. All right? If you have the log of a quotient, a over b, Well, if the product became addition, the quotient is becoming subtraction. So you have the same feature kind of going on. And the last one's the one that starts to look the most maybe like something of a derivative going on from what you've learned now in Calc 1. But if you have the natural log of a power, right, you have something to the n power, it's actually the same as having the product of that power, the exponent, the n, multiplied by that natural log. And again, there's no derivatives here, okay? And I'll show you why this is a helpful feature to know all these log rules when we get to the point where we're taking derivatives, because you're going to want these, I promise. All right, so keep these sort of in your mind as you're working with derivatives, that can I simplify the expression before I work with any logs? Or, sorry, before I work with any derivatives. All right, so did everybody get those written down? Okay. So we're going to do an example. This is actually the natural log of 3e squared. And we're going to use the properties of logs to expand, because that's the one that's going to be the most helpful for us once we start taking derivatives. It's the idea of expanding and condensing logs. So if I have the natural log of 3e squared, what could I rewrite this as? I'm going to have a natural log of what? That's really close. Be really careful. What is the power of 2 applying to? Only to the e. It actually doesn't apply to the 3. So let me take a couple of steps. The first thing I want to take notice of is that there's actually a multiplication here. 3 times e squared. So I'm going to write this as natural log of 3 plus the natural log of e squared, because that squared really only applies to the e. So we want to be careful when we're talking about bringing that exponent down. That's kind of how we think about it, that we bring it down at the right spot. And then we can bring it down, like many of you said we should, and we would put it, but only in front of the natural log of e part. And you might be tempted to leave it there, but there's actually one more thing you can do. Yeah, this piece right here is equal to 1. So this is actually the natural log of 3 plus 2, right? So you have 2 times 1. And as you work through these, however much detail you want to show is fine. Some of you can probably look at that and get most of that done in 1 or 2 steps, and it probably is not going to take you 3. That's okay. But just be careful that you're not missing something along the way and accidentally putting something down in front of something that's not supposed to be done. Okay? Now we're going to do the opposite on this one. We're going to take something that's all expanded and we're going to condense it. That is, we're going to put it back into one expression, one type of a log. All right, so suggestions. What do you see that you might want to do first? We could distribute the 2. That would be fine. We could also leave the 2 where it is. It's an option. I'm going to leave the 2 where it is for the moment, and if you want to distribute it, it's fine. I'll show you what you can do with it. It'll be the same at the end. I'm going to leave the 2 alone. I want to actually start inside the brackets. What could you do? Well, it's not like multiplication. I need to use those expand and condense rules. So now I have the log. Oh, you know what? Let me do it this way. When I have the log of things added or subtracted like I do on this slide, I'm able to combine them back together. And I combine them with what operations?
Multiplication and division.
Either multiplication or division. And the reality is the multiplication or the division actually affect, well, what it's affected by is the sign right here. If it's a negative sign, that's going to go in the denominator of a fraction. And if it's a positive sign, that's going to go in that numerator of that fraction. So what I'm going to do is I'm going to have the natural log of a bunch of stuff. The x is going to be on top because out in front of the x, there's a positive sign. We don't see it, but we understand that it's there. But in front of the other 2 logs, they're negative signs. Agreed? So those are actually going to have the components x plus 1 and x minus 1 in the denominator, and they are multiplied. Another way that you could see that, because some people have difficulty thinking, well, but they look, I mean, it doesn't look quite like that, is that it looks like if you wanted to, you could actually undistribute that negative. If you pulled that negative out, that natural log of x plus 1, that natural log of x minus 1, that's addition. That's why those are getting multiplied together. So you can think about it from that way too. Of course, I'm not done because I had a 2 at the beginning. All right, so Kirsten wanted me to deal with that 2 first, and I actually wanted to wait because now I can do what? Yeah, I can actually just make that a squared on the whole thing, and then I don't even have to distribute that through. It's acceptable to leave that as is. So I could write this as 2 natural log, I'm sorry, I said that wrong, natural log of x over x plus 1 times x minus 1, quantity squared. If you don't want to leave the squared there, you could distribute the square at this point too. So either of these would be perfectly fine ways of writing your final answer. This would be x squared, this would be x plus 1 squared, and then x minus 1 squared. Any questions on that? Do you guys remember some of this stuff? I hope so. I hope this doesn't look like something you've never in your life seen. But we need these for some of the features we're going to be doing later to make our lives easier. Let me show you a couple other properties, ways that you can use this information. Sometimes, and this particular happens on standardized tests. So for some of the tests that some of you might end up taking, you might end up seeing something like this. This is a natural log. They give you the values of the natural log of 2 and the natural log of 3. Okay? So they're not asking you to use your calculator here to find those values. They're just giving them to you. Correct at least to 4 decimal points. And they want you to find the natural log of 2/3. Well, the problem is this does not say natural log of 2 divided by natural log of 3. Do you recognize that? That is not the same expression. This says the natural log of the number 2 over 3. How could I use my properties so that I could use the fact that the natural log of 2 is given to me and the natural log of 3 is given to me? That's close. Is it times? Oops. Yeah, there you go. All right. So it's actually the natural log of 2 minus the natural log of 3. That's what we're going to have. And you have the values for those, right? The natural log of 2 is actually 0.6931. And the natural log of 3 is actually 1.0986. Then if you want to grab your calculators to subtract, that's fine. But you have to show me the step where you separate out the natural log of 2 and the natural log of 3. That's how I know that you're using the properties to do this and not just your calculator to plug in natural log of 2/3. That's a different feature. That's just punching buttons. But what is this if you subtract? What do you get? It's negative something.
Negative 0.4055.
You have that too, Janet? Okay. I got a couple people saying yeah. That looks good, right? So we've subtracted, so we've actually found that value. And we're done with that piece. Now, B is a little different because I don't see any 2s or 3s. But the way that the problem is set up, somehow there must be a way that I could use that given information with natural log of 81. Any ideas? Yeah.
Natural log of 3 to the 4th power.
Excellent. 81 is actually 3 to the 4th power. And if you didn't remember, you could just break 81 down with factoring, right? 81 is 9 times 9. That's probably what you remember. And then 9 is 3 times 3. So it's actually 4 3s. Now what? You got it. So the 4 is going to come to the front. That's another property of log. So we have 4 times natural log of 3. And then what?
4 times the number given.
You guys are following along well. Good. 4 times the number that was given, which was 1.0986. And if we multiply those, what do we get? 4 point something.
4.3944.
Okay, did everybody get that? Excellent. All right. So far, so good? Okay. I'm going to talk a little bit about limits. There are 4 limits written on your page for natural log functions. And you can think about this by flipping back to the very front page where we talked about the graphs of these things. We actually did the first one already. What is the natural log, the limit of the natural log as x goes to infinity? It was infinity. We did that on the slide with the graph, actually. So let me flip back over here. This one was right here written. And if you follow and trace along this direction, you can see that that's what's happening, right? Now, the second one is actually something different. And let me skip that one and go down to the third one and the fourth one first. Do you remember what that notation with the number with a little plus sign or the number with a little minus sign means? What does that mean?
Right.
Good. From the right or from the left? And the way I remember it is the plus sign is coming from the right because that's the positive side of the graph. But it means you're moving left, which kind of tends to confuse people. So if I'm looking at the derivative or the log limit as you move from the right, from the positive side of the graph towards x equals 0, this is the direction I'm moving. I'm actually moving along my graph from the right-hand side towards x equals 0. What's happening? It's decreasing. How far? Yeah, infinity, and it's negative, right? Because it's the bottom part of the graph. So this limit right here is actually negative infinity when the limit is coming from the right. What about the left? Was it? It doesn't exist. Why not?
Because it doesn't come from the left side.
Yeah. Did you guys notice? There isn't anything on the left-hand side of 0, is there? There is no graph over here. There's nothing there. So I can't even talk about that limit because there's nothing there to talk about. Okay? So there's nothing on that left-hand side of the graph. There is no limit as you move towards x from the left-hand side. And because these last two limits don't match, that is, one of them is negative infinity and the other one is does not exist, what happens when you talk about the limit at 0 itself? It doesn't exist either because those don't match. So you can't come at the limit from both directions because there is only one direction that you have part of the graph going on. Okay? So let's take a look then at what happens when we have this limit of the natural log of x minus 6. So let's think about a graph, because that's the easiest way for what we're looking at in this chapter to talk about limits. What will this graph look like? I mean, it's a log graph, but something's going on differently. What? It's moved right 6. So roughly speaking, I have a graph that looks something like this. Imagine that that's dotted and it's at x equal to 6. Okay? Here's my y-axis. Here. And this is x equal to 6. And then what happens? Yeah, my x-intercept is at what number? It would be at 7, yeah. 7, 0. So, this is a sketch, but I'm not asked to graph this, actually. I'm just using the graph to answer the question. So this is the image you should have either in your mind or on the paper. It doesn't matter to me. You don't have to draw it for me, but this is the image you should be thinking of. So what is the limit as x approaches 6 from the right? It's negative infinity. And it's located right here, yeah? I mean, we're moving in this direction down the graph. So this is actually negative infinity. Okay, and the wonderful news is we're actually going to get to derivatives, which is good because this is calculus, and that's a calculus concept. We haven't done any derivatives yet in 5.1. Okay, then, so if I have a natural log of x as my function, what is its derivative? Well, I want to take you back to the very first thing that we did, which was talking about what these functions are. I told you that the natural log of x is defined to be the integral of 1 over x, right? Well, if I were to take the derivative of both sides of this, this would be that's the derivative of ln x. I mean, that's what I'm trying to figure out, right? What is the derivative of ln x? Well, what happens on the right-hand side? Yeah, in some sense, these are opposite operations, right? Derivatives and antiderivatives sort of have that inverse sort of a feature to them. So these sort of cancel each other out. So what's the derivative of ln x? It's actually 1 over x, sort of. Well, yeah, we'll write it as 1 over x. We'll encounter the other issue later. I have 1 over x, but it's actually only defined when x is positive, right? Because the natural log of x was only defined for x being positive. Agreed? I mean, we were only on the right-hand side to begin with, so I can't take a derivative and somehow get to the left-hand side of a graph. That's not going to happen. So this is going to happen when x is still positive values. So let's do a couple derivatives before I let you go today. We've got here the natural log of x minus 1. So what would the derivative be for the natural log of x minus 1? Yeah, it's 1 over whatever is inside of the log, x minus 1. And in this case, we're done because what's the derivative of x minus 1? It's just 1, right? It's a linear function, and I don't think I even wrote the linear function rule up here, but you guys know it, right? It's just the actual number in front of x, so it's 1. So this is actually finished. The next one becomes a little bit more involved. So let me make you aware of a couple features. What's inside of that parenthesis? Division. Which means which of these rules do we very quickly have to handle? The quotient rule. If we do this problem exactly like it's written, this is going to involve the quotient rule. I don't want to do the quotient rule when I don't have to, and I don't have to here. Does anybody else see something you could do? Yeah, and that's the whole reason we wanted to talk about those log properties, is because they're going to make our lives easier. I can split this up into two separate logs. I can write this as the natural log of x minus the natural log of x squared plus 1. Now, do not be tempted to think you can split up the x squared plus 1. There was no property for logs where there was addition inside and allowed me to separate it. I can't do that. But at the very least, I don't have the quotient rule anymore, right? And that's a good thing, because the fewer rules you can apply, the less likely are you going to make a mistake. I mean, you've just got less going on, right? All right, so what then is the, let me get my pen back. What then is the derivative of natural log of x? 1 over x. And what is the derivative of the natural log of x squared plus 1? Yeah, so I'm going to write it in a different order, but you're exactly right, and you can write it that way if you'd like. We've got the 1 over x squared plus 1. This is actually a chain rule, right? So I'm going to use this notation right here. Took the derivative of the outside, so the derivative of the natural log part is the 1 over. And then we have to do the derivative of the inside, and the derivative of the inside is the 2x. So if you were doing the basic skills quiz for me, you'd be done here. There's no simplifying. There's nothing else to do. Remember we talked about those? No simplifying. Yay! Makes it a lot easier to grade too. Just that's a selfish reason, but yeah, we would be done. But you're not done because you're not doing a basic skills quiz right now. You're doing notes in class for preparing for some of your homework, and simplifying is part of the process in doing that too. So your algebra skills are going to get real good. I hope they're good already, but if they're not, they're going to get better. So we've got to somehow combine these back together. How do you combine fractions? You need common denominators. So we're going to take this, and we need some common denominators here. So I need the first denominator to include an x squared plus 1. If I do it to the denominator, I've got to do it to the numerator, right? And then the second fraction needs to have part of its denominator to be x. And if I do it to the denominator, I need to do it to the numerator. So right now I've got x squared plus 1. I've got a minus, and then I've got 2x squared from the second fraction. And all of this is going to be written with the x and the x squared plus 1 not multiplied out. We don't want to foiling is not helpful, okay? That is not going to be helpful at all. Leaving that in factored form is the best option. So we're going to leave that factored in the denominator, but I can simplify the numerator one more time. What do you notice? Yeah, I've got 2x squareds. I've got a positive x squared and a negative 2x squared. So that's actually negative x squared plus 1 over x times x squared plus 1. And I know the numerator and the denominator sort of look like they've got an x squared plus 1 both in them, but the fact is that they don't, because the signs do not match, and they're not exact opposites either. Like I can't factor a negative out and make them match. The best I can do is to leave it written this way. So your actual final answer here for the derivative is this. Any questions on that one? All right.